In the last class, we have seen the 3 steps involved in the steam reforming process. These were feedstock pre-treatment process, the major steam methane reforming, and the third one was water gas shift, also known as carbon monoxide shift reaction. Now today we will see the 4th step in the steam reforming, that depends upon so the last step, which is the purification step, that determines which water gas shift reactor will be there. If it is pressure swing adsorption is the purification technique which is being utilized, then only high temperature water gas shift reactor will be there. However, if there is a change in the purification technique, like if we are using after SMR a high temperature water gas shift, a low temperature water gas shift will be followed if the final purification stage is carbon dioxide solvent based purification technique. To get pure hydrogen. So, if solvent based carbon dioxide removal method is being used, in that case we know that from the low temperature water gas shift less than 1% of carbon monoxide is left, and that can undergo preferential oxidation to convert into carbon dioxide. Now various solvents are being used to remove the carbon dioxide formed, and these the preferable ones are monoethanolamine. This is the most widely being used. Ammonia solution, methanol, potassium carbonates. There are many solvents which are available which absorb carbon dioxide to reduce the carbon dioxide content in the product to about 100 ppm. Now whatever is the left out carbon monoxide and carbon dioxide remaining in the product gas, that can undergo methanation reaction in the methanator to finally convert into methane. So this is one type of purification. If however pressure swing adsorption is used for purification, in that case various adsorbents can be used. So different adsorbents can be used, wherein on the surface of which the impurities like carbon monoxide, carbon dioxide, methane can get absorbed so as to be so that we can remove all these impurities and we can get pure hydrogen as the product. Now the primarily molecular sieves are being used, for the separation of carbon dioxide, carbon based species and get pure hydrogen. Now in these sorbents, adsorption and desorption of the impurities occurs on the change of pressure. That is why the name is pressure swing adsorption. and we can get high purity hydrogen when all these impurities are selectively adsorbed onto the adsorbent surface. After hydrogen product is being obtained, which is of high purity, the remaining off gas or tail gas, that itself has certain amount of hydrogen and it has a calorific value. So, that this off gas or tail gas from the pressure swing adsorption can be used as a fuel in burner in the reformer. So, this is about the purification step involved, the last step in the steam methane reforming. So, we have seen all the 4 steps separately. Now, let us see them together so that we can know what are about the complete reforming steam methane reforming process. Now, as we have seen, natural gas acts as both fuel and feedstock in the steam methane reforming process. So, it acts as a feedstock entering into the desulfurization unit, and it acts as a fuel and supplies the required heat to the burners of the steam methane reformer. In the first step, a small split stream of hydrogen from the product side, it is used for catalytic hydrogenation of sulfur containing compounds on a sulfur tolerant catalyst, which is cobalt molybdenum catalyst, at a temperature of 290 to 370 degrees centigrade, and that forms H2S. This H2S which is formed is scrubbed on a zinc oxide bed to form ZNS and steam. Now, once the sulfur containing impurities are removed in the desulfurization unit, the treated natural gas, it goes to the second step, which is the steam methane reforming process, wherein methane, which is pre-treated, where the sulfur containing impurities are removed, this is preheated and compressed, it is preheated and compressed along with steam at 2.6 MPa with a steam to carbon ratio of 2.5 to 3. An excess of steam to carbon ratio is required so as to reduce coke deposition. These are fed into the primary reformer or the main reformer unit, which is the steam methane reformer. Now, these both the natural gas, preheated natural gas along with steam, this enters into the reformer tubes, wherein it is a catalyst bed containing nickel on alumina, and the reforming reaction takes place, methane reacting with steam to give syngas. Now, these reformers, they depending on where the burners are, these are tubular reformers, tubular box type of furnace, wherein depending on where the burner is located, these can be either top fired reformer, bottom fired reformer if the burners are on the bottom side fired reformer, or terrace fired reformer. In an industrial scale steam methane reformation plant, there are hundreds of such tubes arranged in a reformer, wherein the length of these tubes is somewhere around 9 to 15 meters. Its inner dia is around 7.5 to 12.5 centimeters with thickness of 1.2 centimeter. Now, the heat which is required for the endothermic reaction that takes place in these reformer tubes is supplied by the burning of the combustion of the fuel, which is again natural gas, along with air which is fed to the burners, and on the combustion of it, it supplies the required heat. Now, as we know that it is a very endothermic process, it requires lot of heat. Reaction takes place somewhere between 700 to 950 degrees centigrade, and because the reason for very high temperature is both your feedstock as well as the oxidant, they are inert. So, a large amount of energy is required to make them active and react. In this process of combustion which is taking place in the burner, 50% of the heat which is being supplied is taken up for the reforming reaction in the tubes. However, the remaining heat which comes with the combustion gases or the flue gases, that can also be utilized. So, the rest of the heat is recovered in a heat recovery section, and that heat which is extracted from the reformer, from the combustion flue gases coming out from the reformer, can be used either for steam generation or it can also be used for preheating the natural gas before it enters into the reformer. Now, the next step, as we have seen, is water gas shift reaction, wherein more of hydrogen can be extracted. Carbon monoxide reacts with steam to produce carbon dioxide and 1 more mole of hydrogen. This reaction occurs at a temperature of 340 to 360 degrees centigrade, and this is slightly exothermic reaction. That means it will be favored at lower temperature. However, if we see the syngas which is obtained from the steam methane reformer, the temperature of it is around 750 to 900 degrees centigrade, and the required temperature for water gas shift reaction is approximately 350 degrees centigrade. It has to be cooled down from 750 to 900 to 350 degrees centigrade, and again that much amount of heat is removed and can be utilized for steam generation. In the last step which we have seen today, purification step, finally the syngas obtained after water gas shift, the product gas obtained after water gas shift goes to the pressure swing adsorption unit, wherein there is actually it is a batch process. However, using multiple adsorbent beds it can be made continuous, and after PSA we get pure hydrogen with a purity of 99.999% pure at a pressure of approximately 14 bar. However, there is still sufficient amount of hydrogen and other gases which have a certain calorific value are there in the tail gas or PSA off gas, that goes to the burner of the catalytic reformer, steam reformer, and can be used as a fuel for the heating up of for conduction of the endothermic steam methane reforming process. So, this is all about the reforming process. However, catalyst is an important part of the steam reforming reaction, and we know that catalyst is actually a substance that increases the rate of the reaction, but it is not consumed in the reaction. When it comes to steam methane reforming, there are several requirements that the catalyst need to meet out, like it should be robust, under the stringent operating conditions, conditions like at the inlet of steam reformer the temperature is about 450 to 650 degrees centigrade, at the outlet it is 750 to 900 degrees centigrade, and the catalyst has to sustain under these temperature gradient temperature conditions. It should have high catalytic activity, it should be thermally and mechanically stable, it should show acceptability towards certain change in the feedstock. So, a variety of feedstocks, definitely long cycle life is important, cost it should be less expensive, low in terms of cost. It should also show stability under transient conditions. at the time of startup or shutdown. Under those transient conditions the catalyst should be stable enough. Pressure drop across the deformer should be lower in the catalyst bed, and its heat transfer characteristic should be good. So, these are the requirements in terms of the catalyst. While selecting a catalyst, it ideally should meet out these requirements. We know that when we are talking about a catalytic process, in the catalytic process on the surface of the catalyst, the reactants they adsorb, they undergo different reactions, the bonds are formed, bonds are broken, and finally the product is formed and the catalyst returns back to its original initial state. So, various steps which are involved in a catalytic process is, first is the bulk diffusion, wherein the reactants they reach the catalyst surface. Thereafter the catalyst get absorbed on the active sites of the reactants get chemisorbed onto active sites or nearby sites of the catalyst. In the third step, bonds break and bonds are formed, leading to product formation. Once the product is formed, thereafter the product has to desorb. From catalyst surface. Finally, it has to undergo the bulk diffusion from surface into the catalyst bed, going into finally the again this finally diffuses into the mainstream of the product gas. Now, if we see these processes, process 1, process 5 and process 6, these are actually sort of physical processes wherein these depends upon the physical properties of catalyst, of active, of support and the media. However, if we see the process 2, process 3 and process 4. So, process 2, 3 and 4, these are chemically activated process. Where reactants are consumed, conversion of reactants takes place, formation of product takes place, formation of various intermediates before the formation of product occurs. So, as such the chemical properties, the interaction between the support, the catalyst support and reactants to form product is more important. Now, in a catalytic process, any of these reactions can be the rate limiting step. In the whole process, any of these out of the 6 processes can be the rate limiting step. Now, let us come back to the steam methane reforming. We know that the catalyst plays a dominant role. It is not only catalyst alone, but the support and the promoter that also plays a dominating role. Now when we talk about industrial scale hydrogen production using the steam methane reforming, primarily the catalyst which is being used is nickel. So there are several advantages of having nickel catalyst, that it is showing activity which is good, it is stable under the operating conditions and it is low cost. However, at the same time there are certain disadvantages or issues associated with the nickel catalyst, that it is more prone to deactivation and sintering. So in that case there are several other catalysts which has also been looked at by the researchers, including the noble metal catalyst, ruthenium, rhodium, iridium, platinum, palladium. So these are the catalysts which have also been looked at for the reforming reaction. But the major issue that comes in while using on an industrial scale is the high cost of the catalyst. Now there are several factors which also affect the heat transfer, the pressure drop, the conditions inside the catalyst bed, and primarily if we look at the catalyst design, we have to consider the factors like what is the shape of the catalyst, what is the size of the catalyst, surface area associated, the methods by which these are synthesized, that also affect the catalytic process. All these factors can affect the pressure drop, the heat transfer characteristic from the reactor walls to the from the reformer tube walls to the reactant. Like if we see the pressure drop, now if size has a very important effect in the pressure drop. So what we want is the pressure drop in the catalyst bed should be low. Now but this pressure drop, it depends upon what is the void fraction inside the catalyst bed. And if the particle size of the catalyst is lower, then we can see that the pressure drop inside the bed will be higher. So there should be an optimum, because we want better heat transfer, at the same time we want a lower pressure drop. So the void fraction should be higher. In order to keep that, we need to optimize the conditions inside the catalytic bed. The shape of the catalyst also affects the reforming reaction. Herein there are several shapes which has been looked at, like rings, cylinders, cylindrical shape with holes. Then there are gear wheel type of catalyst, gear wheels type of catalyst, spoked wheel type of catalyst, multi-channel catalyst have been used. They all having holes so as to have the required flow of the gases inside. Most widely used one are the multi-channel catalyst having several holes. Size again is important here. The size determines the pressure drop, at the same time it will also determine the heat transfer across the bed. Now for example, if size is lower, for small size of the catalyst, heat transfer will be better, but at the same time pressure drop will be higher. So there should be an optimum size of the catalyst to be decided so as to have a lower pressure drop, at the same time having a higher heat transfer characteristics. Usually the catalyst are supposed to operate for stably for long hours. Typically about 5 years of continuous operation is required without any loss of the activity. Now other than the catalyst, support again is very important and that plays a dominating role. There are several requirements which even support for the support when it is to be used along with the catalyst. We know that support should have a very good dispersion. It should stabilize the catalyst. It should ensure high surface to volume ratio. It should withstand the conditions of operation inside the reformer. It should provide good interaction between the reactants and the catalyst, and that will reduce the catalyst deactivation and sintering. So these are ideally the requirements when a catalyst support is being looked at. For industrial scale hydrogen production, mostly nickel on alumina support is being used as a catalyst in the reformer tubes. Other than alumina, there are several other catalyst support which are being studied, like magnesium oxide, magnesium aluminium oxide, zirconia, titania, ceria. These are the other support which are being studied and reported in the literature, perovskites. Now each of these, they have their own characteristics. Like alumina, it has slightly acidic character, acidic in nature, and that helps in reforming, that promotes reforming reaction. However, if we look at magnesium oxide, then this reduces coke formation or it promotes the carbon gasification reaction. Zirconium oxide, that has good performance. So all of these supports have their own characteristic. Cerium oxide, this is less prone to coking. So these are the characteristic of these support materials which have been studied in literature. Now other than the catalyst and support, promoters, a small quantity of promoters are added, and this addition of promoters, this suppresses coke deposition onto the catalyst surface. The catalyst, the subpromoters are used including alkali, metal, elements like potassium, alkaline, magnesium and calcium, transition metal based. including molybdenum and tungsten from the lanthanide series. Lanthanum and cerium. So, when a small quantity of these promoters is being added, this is beneficial and reduces the carbon formation in the on the surface of the catalyst. Now, if we look at the catalyst, the major problems, challenges which are associated with the catalyst bed, then there are many factors that needs to be taken care of. The primary constraint is the catalyst poisoning or deactivation, which is basically caused because of the presence of impurities, because of the carbon deposition. Now, these carbon deposition has a substantial effect onto the catalyst deactivation. Now, what that leads to is either it can cause partial or complete blockage of the reformer tubes, and when it causes blockage of the tubes, there will be a pressure drop, uneven flows will be resulting, gas flows, and that uneven gas flows can result into formation of hot spots, can increase tube wall temperature, which is highly undesirable. Uneven fluxes, and that can even lead to at times tube failure. So, this catalyst deactivation is a highly undesirable when it is into the reforming reaction. However, the carbon formation, it has been known from the thermodynamics that it takes place at a lower temperature, below 500 degrees centigrade. There can also be problems associated with the catalyst breakage, and that catalyst can break under transient conditions. The breakage is mainly observed when it is either starting up or shutting down of the reactor, and then the catalyst can lose its mechanical strength during that, or it can be because of the pressure which is exerted. Inside the reformer tube, there can be certain thermal stresses. If there is a cooling, that can lead to catalyst breakage, and this is always undesirable in the reforming process. What is actually required is a uniform catalyst loading, and that can lead to stable operation over longer duration, prolonged operation. If however, there is a non-uniform catalyst loading, then that non-uniform catalyst loading can again give rise to several issues. There will be uneven flows, there will be temperature gradients that will be there, there will be pressure drop, uneven pressure drop inside the column, hot spots will be created, and that can lead to tube damage and reduced tube life. So, that is highly undesirable. Besides these, there could be a problem which is associated with the catalyst settling, and that can also create problems. Now, what are the ways to address these? The ways to address these problems is, first is we have to select the appropriate combination of catalyst, support and promoter. Other than that, the design of the reactor of both reformer and tubes is very important. Now we can about the catalyst deactivation. Deactivation can be reduced or the carbon formation can be reduced by high steam to carbon ratio, and ideally it should be somewhere between 2.5 to 3. At the same time, with the proper choice of promoters, carbon formation can be reduced. If there are higher hydrocarbons, present, then a pre-reforming unit is essential. And the use of noble metals or bimetallic although these are expensive but could be beneficial against the carbon deposition. Now we have seen that there are challenges associated with the reformer, and the major limitation in the reformer, it seems that the catalytic activity could be the major challenge, but it has been observed that the catalytic activity definitely could be the rate limiting step, but at the same time the heat transfer characteristics, the heat transfer is prominently or the major limiting factor when it comes to the operation of a steam methane reformer. Now although the catalytic activity decides the rate of the reaction, but the heat transfer that is found to be the major rate limiting step. So when it is up to designing the reformer, a proper heat transfer or thermal management is essential, is very important. At the same time, the thermal conductivity of the support is also important. Now when it comes to designing the reformer, there are several heat transfer considerations that need to be taken care of, and these design considerations that need to be taken care of includes the temperature, the pressure that will be there in the reformer, the material with which the reformer tubes are being made, their rupture strength. So the materials which are highly temperature resistant could be used for making the reformer tubes that can sustain such high temperatures and pressure. Now when heat transfer calculations are being done, then we have to see the heat transfer not only from the burners, but till the point it goes to the reactants, that heat of reaction goes to the reactants. So all the heat transfer aspects needs to be considered. Radiation which is taking place from the walls of the tube, walls of the tubes and the reformer. Then comes the convection from the gas, the combustion gases, the flue gases to the tube walls. Conduction across the tube walls. Convection from tube walls across the catalyst bed to the catalyst and to the reactants. So, all these aspects needs to be taken care of while designing the reformer and reformer tubes. Now, besides these major heat transfer considerations, also the reaction kinetics, how the kinetics of the reaction inside the tubes is, what is the interaction of the catalyst with the different reactants, what is the heat and mass transfer limitations within the tubes, that are also need to be taken care of. However, in a well designed reformer, it is observed that under stable operations this is not much of a problem. However, the major problem arises under the transient conditions of starting up as well as shutting down. So, this is all about the steam methane reforming. So, in the today's lecture we have seen the entire steam methane reforming process considering all the 4 steps. Thereafter we have seen what are the different catalyst support promoters which can be used. We have seen what are the requirements in terms of the catalyst as well as support, what are the different design considerations that needs to be taken care of while selecting a catalyst, selecting a support. Also the heat transfer characteristics of the reformer, what are the various parameters that needs to be taken care of while designing the reformer and reformer tubes. So, thank you.